Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello ladies and gentlemen. First of all, I would like to say thank you to Committee in International Conference on Digital Transformation in Business and Organizations. Today, I will present our study entitled Big Data Analytics Integration in ISO 9001-2015 Quality Management System, a dual method systematic and bibliometric analysis. And the members of authors team are Yosep Hernawan, Dian Addinna, GIlang, Garnadi, Suryadi, and Rasto. We are from Universitas Pendidikan Indonesia. Okay, over the last decade, manufacturing organizations have rapidly adopted advanced technologies such as artificial intelligence, machine learning, Internet of Things, and big data analytics. This technology promise predictive quality control, real-time monitoring, and data-driven decision-making. However, our review shows that Quality 4.0 is frequently treated merely as a technological upgrade rather than a systematic transformation. In other words, organizations are becoming better at developing algorithms but not necessarily better at integrating those algorithms into auditable and standard-compliant quality systems. This creates a disconnect between technological capability and quality governance. As a result, many organizations possess sophisticated analytical tools yet lack a structured framework that links those tools to ISO 9001 requirements, risk-based thinking, and evidence-based decision-making. This disconnect became the primary motivation for our study. To investigate this issue, we conducted a dual method analysis consisting of a systematic literature review following PRISMA guidelines and bibliometric network analysis using PostViewer. Our dataset included 142 peer-reviewed manufacturing studies published between 2021 until 2026. Our remarkable finding is the rapid growth of research activity. Almost 40% of all publications appeared in 2025, while more than 83% of the total evidence base was produced during the last 3 years. This indicates an explosive increase in academic and industrial interest in big data and Quality 4.0. To strengthen reliability, we cross-validated findings using both methods. The result was 89% convergence between systematic and bibliometric analysis, demonstrating that the patterns identified are not methodologically artifacts but genuine structural characteristics of the field. Among the 142 articles reviewed, 71.1% focus on artificial intelligence and machine learning implementation. Only 2.1% explicitly address integration with ISO 9001-2015 requirement. This produces a striking 34-to-1 disparity. In practical terms, for every study investigating ISO 9001 integration, there are approximately 34 studies investigating AI and machine learning. This demonstrated that researchers and practitioners are prioritizing technological capability while largely neglecting quality system integration. The implication is significant. Organizations may become technologically advanced without becoming quality system mature. Technology is growing rapidly, but compliance-oriented quality architecture is not keeping pace. Our bibliometric network analysis further confirmed this problem. We identified several thematic clusters within the literature. The AI and machine learning cluster emerged as the dominant research area. In contrast, the quality management system cluster was relatively small and weakly connected. Specifically, AI and ML appear in more than 71% of studies. Quality management system appear in only around 12%. The weak connectivity between this cluster suggests that researchers tend to discuss technology and quality management as separate domains rather than integrated systems. This is exactly what we call the technology QMS gap. The challenge is no longer whether AI works. The challenge is how to aim AI into an auditable standard-based quality management framework. Surprisingly, none of the 142 studies measure overall equipment effectiveness or OEE as composite metric. As a reminder, OEE consists of three components: availability, performance, and quality rate. Yet our analysis found 0% measure composite OEE, only 2.1% measure individual OEE components, and only 5.6% assess customer satisfaction within a formal ISO 9001 context. This reveals a significant measurement gap. Researchers are developing increasingly sophisticated algorithms, but they are not consistently measuring outcomes that matter most to quality managers and auditors. Without common performance indicators such as OEE and customer satisfaction, organizations struggle to evaluate whether digital transformation actually improves quality management effectiveness. One of the most interesting findings from our review is that technology itself is not the primary barrier. The biggest obstacle are organizational and human factor. The most frequently reported barriers were resource constraints appearing in 37.3% of studies, training and capability gaps appearing in 18.3%, and infrastructure limitation appearing in 14.8%. Conversely, the most important success factor included capability development, fast information approaches, leadership commitment, and strong technological infrastructure. These findings suggest that organizations should not begin their transformation journey by purchasing expensive technologies. Instead, they should first invest in people, skills, governance structure, and organizational readiness. Human capital development must precede technology procurement. To address these challenges, we synthesized evidence from all 142 studies and developed a new framework called the BDQMS transformation model. This framework is significant because it is the first model that explicitly linked to big data analytics, ISO 9001-2015 requirement, and PDCA cycle. Rather than treating technology as a separate initiative, the model integrates technology directly into quality management process. It provides organizations with structured roadmap for implementing digital transformation while maintaining appliance with ISO 9001 standard. 5-layer transformation model. The BDQMS transformation model consists of 5 sequential layers. Layer 1 is foundation, focusing on governance and leadership. Layer 2, integration, connecting IoT system, ERP platform, and QMS process. Layer 3 is intelligence, where AI and machine learning capabilities become operational. Layer 4 is optimization, where intelligence is used to reduce defects and improve performance. Finally, layer 5 is evolution, enabling continuous learning and adaptation toward Industry 5.0 readiness. The layer structure emphasizes maturity progression. Organizations should not jump directly to advanced AI implementation without first establishing governance and integration capabilities. The first layer corresponds primarily to the planned phase of the PDCA cycle. Layer 1, foundation, focus on leadership commitment, data governance, strategic alignment. This layer maps directly to ISO 9001 clauses 4 and 5. Layer 2, integration, focus on IoT deployment, ERP connectivity, and integration of digital system with quality processes. This layer maps to clauses 6 and 8. For manufacturers in developing economies and organizations with limited resources, these two layers provide the most practical starting point. Before implementing advanced analytics, organizations must first establish a reliable data and governance infrastructure. The next two layers correspond to the do and check phases of PDCA. Layer 3 intelligence introduces predictive analytics, machine learning, data-driven forecasting. This layer aligns to ISO Clause 9, which focuses on performance evaluation. Layer 4 optimization applies this insight to process improvement, defect prevention, operational excellence. This layer aligns with Clause 9.3 and 10. The key principle here is accountability. Artificial intelligence should not exist merely to generate prediction. It should generate measurable quality improvement linked directly to organizational objective and quality metrics. The final layer is evaluation. This layer represents the phase of PDCA and align with ISO Clause 10.3 on continual improvement. At this stage, organization aims continuous learning into the quality management system itself. Rather than reacting to problems after they occur, the system becomes capable of adapting proactively through data-driven feedback loop. This creates the foundation for Industry 5.0 readiness, where human expertise and intelligence systems work together to achieve continuous quality improvement. To ensure practical relevance, the BDKMS transformation model was validated using a Delphi process. 12 expert participants, including quality managers, digital transformation leaders, academic researchers. They represent multiple sectors, including automotive, electronics, pharmaceuticals, and food manufacturing. After 2 rounds of evaluation, the model achieved 92% consensus. This high-level agreement indicates strong confidence in the framework structure, the sequencing logic, and the ISO 9001 clause mapping. Therefore, the model is not merely a theoretical construct, but a framework supported by both evidence and expert judgment. In conclusion, our study identifies 2 critical gaps. First, the integration gap demonstrated by the 34:1 disparity between AI research and ISO 9001 integration research. Second, the measurement gap demonstrated by the absence of composite OEE measurement and the limited focus on customer satisfaction. The key message of this presentation is simple. Compliance and evidence analytics should not be viewed as competing priorities. Instead, they should be implemented as interconnected layers within a unified transformation strategy. Therefore, we recommend 3 actions. First, stop treating AI as a standalone technology project. Second, re-anchor digital transformation effort to meaningful quality outcomes such as OEE and customer satisfaction. Third, adopt the BDKMS transformation model as a structured roadmap for pace and standard alignment. Okay, I think that's all my presentation for today. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.